Hi everyone, my name is Cinzia and I'm a graduating senior at UMass Amherst. The goal of my 5-college digital humanities project was to incorporate digital humanities technologies with traditional archaeological methodologies to study the water and waste management system in Roman Tharros. The project is titled The Infrastructural Landscape of Ancient Tharros, a GIS approach to recording a Roman city, because I used a combination of archaeological ground survey and modeling in GIS, which stands for Geographic Information System, to carry out the research for this project. I would like to mention that I provided a link to the Tharros Archaeological Research Project's ArcGIS map in which some of my data is shown. If anyone wants to explore the landscape a bit more during this presentation, they are encouraged to do so since I will make several references to the map. I first wanted to talk about the role of digital humanities in archaeology. Advances in technology have been rapidly changing the field of archaeology and how we collect, analyze, and share data. In particular, drone imagery, photogrammetry, and GIS are what allowed me to conduct this research. A large portion of the project was made possible by drone-captured imagery. High-resolution drone photos were stitched together using photogrammetry to create the digital outputs of the orthophotos. These orthophotos are able to be imported into GIS so the site can be observed in detail from my desk in Massachusetts well before I was even able to step foot on site. A portion of this orthophoto is provided on the slide, but a full version can be accessed through the ArcGIS online link. The layer list in the top right corner is where the different layers on top of the orthophoto can be turned on or off. Through this technology, elements of the drainage system within the city can be identified remotely. Prior to this, the best way to visualize distant areas was with Google Earth, but is in no way as complete or high of a resolution as the orthophotos. By importing the orthophotos into GIS, I was able to locate and map the excavated drainage features of the site, such as sewers, drains, and cisterns, which were then modeled and labeled in the map. In the online version, the legend on the top right explains the symbologies of each feature displayed. In addition to the orthophotos, photogrammetry can also output a digital elevation model, or DEM, of the site that shows the changes in elevation across the landscape. In combination with the locations of sewers drawn into the GIS, the DEM was used to map the direction of water flow once it reached a street or sub-street sewer. Additionally, the DEM allows for measurements in meters above sea level to be made. Elevations of specific points along the sewers were taken to help calculate the flow rate of water within segments of those sewers. Though an array of data can be obtained through the orthophotos, there were several features I was not initially able to identify, so a ground survey of the topography was necessary to fully document the sewer system. Last summer, I was fortunate to be part of the Tharros Archaeological Research Project as a member of the project's geospatial team. While on site, I was given time to document the drainage features throughout the city. To do this, I built a FileMaker database and interface for collection that included a record for each feature identified. In total, 46 unique features were recorded, as well as 209 media files, including photos and videos of the features. This allowed the site to be revisited in detail so additional features could be added to the model and analyzed as part of a larger system. This slide shows some more photos taken during the ground survey. The rightmost photo is the view inside one of the sewers, whereas the photo on the top left is an example of the paving that would have covered a sewer. Additionally, the two photos on the bottom left are an excavated sewer which has now been covered with wooden boards, and a drain along the street of the same sewer. With this collection of information, the city was then divided into drainage basins, which are shown in the slide. Drainage basins are divided portions of the city that reflect how the drainage system operated by indicating how the path of rainfall was directed after it landed on roofs and streets. Due to the time available, I am not going to address how I came up with individual basins, though it was a well-considered part of the model. However, I would be happy to answer questions about it during the Q&A. The lines within the basins represent the general direction of water flow within each basin towards a particular sewer. Stippled areas are basins that either drain directly into the ocean, are permeable areas, or have scant archaeological evidence, making it difficult to extrapolate it within the model. Furthermore, the gold dots along the basins are called collection points. A collection point is an abstraction used to indicate the location where all the water that could have been collected from a basin has combined and can be calculated. This was tremendously useful in calculating the volumes of water at various points in the sewer system. Finally, the last portion of the model was building the superbasins. Superbasins are a collection of basins that contain one or more downhill paths throughout the city by which water leaves it. In most cases, the water leads directly through an outlet or out a city gate. Defining superbasins is important since it makes it easier to determine the volumes of water filling sewers along specific paths and observe how much surface area is being directed through a particular outlet out of the city. To save time and also not veer away from the digital humanities focus of this presentation, I will skip the formulas used to calculate volumes of precipitation during rainfall events, the flow rate within the sewers, and the volumetric flow rate of sewer outputs, but I will talk about how they all added to an interesting result. These calculations aided in determining volumes of water in each sewer during specific rainfall events, and test whether extreme weather conditions would cause breakages in the system, causing sewers to back up or overflow. The results of the calculations for the entirety of the city show that it is difficult to encounter a situation in which a section of the sewer system will overflow. Out of 74 collection points, only 7 of them had a rate of change that was close to approaching a breaking point. Out of these collection points, E31 is at the highest risk, but it needs a precipitation rate of 0.053 meters per hour to overflow. Though this is what it would take for the sewer to fail, it is an unlikely and extreme rainfall scenario, and the other collection points needed even higher amounts of precipitation to fail. Additionally, it is interesting to note that collection point E31 is part of the final segment of Sewer 11 along the eastern edge of the city. Not only is all of the water upstream from its respective superbasin eventually flowing through this collection point, accommodating a total surface area of 49,379 meters squared, but the area also has a very weak slope of 0.1 meters. This large volume of water and low flow velocity heightens the risk of overflowing at this section of the sewer. A clear next step in this research is to get more data through additional ground surveys of the topography, which I plan to do during the Tharros Archaeological Research Project's 2021 field season, and revise the model accordingly. On-site, more depth and width measurements will be taken to model the cross-sections at each collection point within the sewer system to be better able to model trends within the structure. For clarity, I will also label the different paths and subpaths within each superbasin and denote them by color. Additionally, further study will be done on the cisterns within the site. Since they are modes of collecting water, the volumes of water they collect will need to be subtracted from the total volumes of water leaving the basins. Finally, study and modeling of the 3 bath complexes in the city will also be important to understand how they contribute to the volumes and paths of water within each superbasin. Their respective basins and water flow calculations will be adjusted as needed. During this research, it has been clear that more sophisticated modes of calculations are needed to more accurately model the performance of intersecting sewers during various rainfall events. Future calculations will have to be done using civil engineering software, so inputs from multiple directions can be calculated. Potential software packages for this task include HEC HMS, StormCAD, and WaterCAD. I would like to conclude by saying thank you all for listening, and thank you to Evan and Professor Paler for organizing this remote event.
Andy Anderson asks, were the sewers only used to collect rain, or did they also collect quote-unquote refuse from buildings?
Yes, they also did that, especially because I modeled the drains that were coming from the insides of buildings and connecting into sewers. The refuse from the buildings, though, wasn't what I was focusing on primarily within the model. I was focusing more on how rainwater is being redirected off of the roofing in the streets. But yes, they did have an impact in the sewer system as well.
Not everyone will know this, but I'm also Cinzia's thesis director as well. So I'm going to take an opportunity as both her thesis director and digital humanities program director to ask her a question about the way in which you've chosen to visualize your information on the map. And I know the decisions that went into that, and I wonder if you have plans or imagine other ways to try to make your information understandable through the map. Let's see what you say.
So a way to make the map a bit more human readable and more visual is thinking about colorizing more the paths in which water is flowing and in their volumes. So something that I've been working on is thinking about doing a color gradient within the super basins to show how water is like building up and connecting as they flow through the city. Another way to do this is to also label all of the slopes within sections of the sewers so that it'd be more readily available to see how the water, even within the system, is either slowing down or speeding up as it's flowing down throughout the city. Because a lot of the quote unquote like problem areas that I was noticing was the ones that had very weak slopes, which the topography was a bit irregular at Tharros. So you can have a very small slope at any point in one of the sewers. So it'd be very interesting to kind of visualize that as well in the model.